Let us start this afternoon's session. The first speaker is Professor Adrien Dubouloz. And the title of his talk is Fake Real Euclidean Planes. Oh, yeah.
So, this is the title. And first, I would like to thank the organizer for the invitation to stay in this place, which turned out to be very convenient to work, and for the opportunity to give a talk here. So, the talk will be about fake, real Euclidean planes. So, typically, I should start with some kind of serious motivation for studying this kind of object. The point is there is no serious motivation. It started like a joke with a colleague of mine, which I visited 8 years ago. Is an algebraic geometry, more an affine algebraic geometry, and we say, hey, it would be fun to mix two unpopular subjects in algebraic geometry, so let's try to do real affine algebraic geometry. And so after a while, we ended up with something which looked like some kind of natural question. So mostly it would be a question of real affine birational geometry, and essentially there is no such thing as birational affine geometry. I will try to explain the flavor of this thing. So the point is we deal with real algebraic varieties. So let me quickly remind you what is a real algebraic variety so that everybody can feel comfortable with this. So a real algebraic variety, there are many ways to define this correctly. If you're not afraid of walking over a non-closed field, you can just say is a scheme of finite type defined over the real numbers, right? It's an R scheme of finite type over the real. And if you want to see this in more concrete terms, this just means say it's a C-infinity manifold. Say, okay, for the whole talk, everything will be about smooth schemes. You can just say it's some kind of smooth C-infinity manifold which can locally be defined as the vanishing of a finite collection of polynomials with real coefficients. Okay. But there is probably one more geometric way to see this, is the same as a smooth, say quasi-projective, just for simplicity reason, smooth quasi-projective complex algebra, quasi-projective and algebraic variety with an anti-holomorphic involution. So some things like z goes to z bar. And then the correspondence is just given by, if you have such an x, you can look at, basically by definition, the set of real points of this x is the fixed locus of the involution. And you go from one side to the other by extending the scalar from R to C, right? And this x of R is exactly the set of R rational points of this guy. While if you look at all complex points, there are complex points of this R scheme. Okay. And this point of view is the one I would choose for the talk because I want to speak about topological properties of real algebraic varieties. So here you have the natural transcendental topology, and you can induce a topology on the set of real points. So everywhere we would have smooth manifolds. So, And in particular, if M is a C-infinity manifold, a real one, then a real algebraic model of M, well, this is just X, a real algebraic variety. Smooth one again, I said that, a real algebraic variety plus a diffeomorphism from M to the set of real points of this guy. So one natural question is whether every infinity manifold admits a real algebraic model, for instance. If it admits one, then basically it's non-unique. It's very non-unique. Okay, simplest example, you take, I don't know, RPN, so the real projective space, then there is a natural real algebraic model, which would be CPN with the standard complex conjugation. And if you prefer this way of stating things, I'm just looking at what should be written PNR, so which is just proj R. And this guy is just extending the scalar and putting the standard complex conjugation. Okay, let's look, for instance, at S1 cross S1. Then a natural algebraic model of S1 is CP1, right? So this guy goes to P1C cross P1C, well, CP1 cross CP1, and in the other language, this corresponds to P1R cross P1R, right? A funnier example, okay, the Klein bottle. So you know this is this non-orientable, this first non-orientable surface which has the structure of a circle bundle over the circle with a non-zero Euler class. The real algebraic model is just the first Hilbert surface F1, which you view as the blow-up of CP2, blow-up at an irrational point. And I could continue the list. So there are many infinity surfaces which have natural algebraic models. Well, of course, you can take Rn and put it into Cn with the standard conjugation, things like this, which would correspond to taking A and R as an R scheme. Okay, but there are many ways to cook up new real models from a given one. For instance, say, so we start with RP2 inside CP2 with the standard complex structure, standard real structure, standard complex conjugation. And what we do here is blow up a pair of non-real conjugate points. So I'm blowing up an orbit of the real involution. So this guy is certainly a real algebraic variety, and if you prefer to view everything in the R scheme context, I just having P2R, and what I'm doing is blowing up a C-rational point. I'm not blowing up an R-rational point, but a C-rational point. So this corresponds here to blow up a pair of complex conjugate points, which are not real. So by doing this, I'm just replacing a pair of complex conjugate points by two copies of P1R, which are conjugate to each other. So I'm not changing the real locus, right? The real locus is exactly the same as mutation, and this is just RP2, right? So this is one way you can cook up other models. And you can try to do exactly the same for R2, for instance. So you go from R2 to C2 with the standard involution. And now you have many other things you can do. Say, blow up pair, say Q bar, so a pair of non-real complex conjugate points. This gives you one other model, and for the same reason as above, the real locus of this guy is still the same, is still R2, or I could just remove a pair Q bar. Well, I'm removing a pair of complex conjugate points, so I'm not changing the real locus, right? Or I could, so this would give me some X2, and then I could just remove a pair of disjoint complex conjugate lines. For instance, remove L bar, disjoint conjugate lines. Well, so I'm removing two lines of complex conjugate point. I'm not changing the real locus. Okay, so what you see from this kind of consideration is that if you want to classify real algebraic models of a given infinity manifold, you have to impose some condition, right? Because otherwise, there are too many of them to get a reasonable class. So the idea is to put topological constraints on the models. So in some sense, we will look at real algebraic model of a given variety with the smallest, the simplest possible topology, right? The smallest topology. So you see, when I'm passing from this guy to this one, I'm blowing up on this complex algebraic variety, I'm blowing up a pair of points. So I'm increasing the H2 by 2 copies of Z, right? Here are the same will occur. So I'm starting with something which has no topology, it's contractible, and if I'm blowing up things, I'm increasing the H2, putting 2 copies of Z inside. Now if I remove points, I'm creating some H3. I have 2 copies of Z inside the H3. So I modify the topology, and if I'm going to remove pairs of lines, I will create some H1. H1 will be Z plus Z again in this case. So the idea is put restriction on the topology. What are the given real algebraic model of a infinity manifold with the minimal possible topology? And for example, so CP2 is the only rational real algebraic model of RP2 with minimal H2. Well, H2 is the same as the Picard rank, and what is hidden in this statement is the fact that every rational algebraic model of RP2 is obtained from CP2 by doing this kind of blow-up construction. Okay, and I said rational. So you could try to look at models, algebraic models of CP2, of RP2, which have the same homology as CP2. So they are fake projective planes, right? What about fake projective planes? And so we heard about this in previous lectures by Professor Keum. So there are smooth, compact, complex surfaces with the same Betti number as P2. And the question is whether they can be equipped with a real structure or not, for instance. And then you can try to decide if they contain RP2 as their real locus. But we know that by classification, all of these fake RP2 are coming in pairs, one and its complex conjugate. So there is no real structure on these fake projective planes. no real structure. So in particular, if you are looking for a real algebraic model of RP2 with the same topology as CP2, then you just have CP2 with the standard anti-holomorphic involution. Okay, and well, there is some kind of complete classification of what can be the smooth, rational, projective model of surfaces, right? And now I'm interested into this question, and this is where we are doing affine geometry. What for R2? Okay. So here we are looking for smooth, complex, complex surfaces with minimal topology with real locus is R2. So what do I mean by minimal topology? It depends on what you prefer to put as a restriction. So you could just ask that the inclusion of R2 in this S sigma as the real locus is a homotopy equivalent. That would be the stronger thing. So in other words, I'm asking that this complex surface is contractible, right? But to give myself more freedom, I will just assume that it induces an isomorphism on homology with integral coefficient or rational coefficient. Okay. So in other words, I'm looking for models which are q-acyclic complex surfaces with a real structure. So now I can give you exactly what is the definition of a fake real Euclidean plane. So definition, smooth, complex, quasi-projective surface S with a real structure is a fake Euclidean plane if, three conditions. First, S is a real plane, real Euclidean plane. By this, I mean that the real locus of R is diffeomorphic to R2. It has minimal topology. So in the sense that hi of S Q, say, is 0, so it's q-acyclic, or it could be z-acyclic, or it could be contractible. It depends the class you want to restrict to. And the first thing why it is fake, which means that S is not isomorphic to C2 sigma as real algebraic variety. Which means equivalently that if you view this guy as a scheme over the real number, equivalently, S is not isomorphic to A to R as an R scheme. I mean, I'm constantly trying to switch between the two types of language. It depends what you want to use in proof. Okay, so the first thing to do is to ask whether such things do exist at all. So existence. Right, because might just happen that we are exactly in the same situation as here with A2, and by putting restriction on the topology, we killed all these type of constructions. And so it could just be that the only real algebraic model of R2 with minimal topology is A2. Well, the answer is no. Here is the first example. So you take this innocent surface S, affine surface, defined by this equation. So this is in C3. This is undoubtedly defined over R because it's defined over natural numbers. And well, I claim that S of R is R2. Well, look, why is nothing, if I'm sticking to real points, why is nothing by the cubic root of x squared z plus x? So I have a parametrization of the set of irrational points of this guy by just sending xz in R2 to x cubic root and z in S of R. So at least it is a Euclidean plane. And another point is you can just compute the topology of this guy to see that the H1 is Z3, the H2 is 0, this is known as pseudo-plane where it's connected, and since it is an affine variety, it has no topology higher than half of the dimension. So, okay, the second condition is satisfied, topology is minimal. Yeah, well, and of course, the last one is satisfied because the first homology group is non-trivial. So this is the first instance of a fake plane, right? So let me give you a second example. So I should call this a real model of the Ramanujan surface. So the construction is the following. You start from CP2 with the standard real structure, and you take the following configuration. So the first thing is cuspidal cubic, defined over L. So it could just be x squared z minus y cube is equal to 0. And now you take a general irrational point. And you look at the conic, the osculating conic to this cuspidal curve at that point. So that's my cuspidal curve, and I'm taking the osculating conic. So this is the conic which is the most possibly tangent to see at that point. And the thing is that the intersection multiplicity here will be 5. And since this is an irrational point, the last other intersection point is necessarily irrational too. So I'm getting two, say PQ, two irrational points. And now what I'm doing is I'm blowing up this point, blow up. So what I'm getting is I'm blowing up an irrational point. So I mean, the first is a Bro surface F1 with the standard real structure, and the exceptional divisor over this guy is the negative section here. And I set S to be the complement in this here's a Bro surface. Let's do this conic Q of the union of the proper transform of C and Q. Okay, C, Q were defined over R. I'm blowing up an irrational point, so everything is defined over R. So this S inherits the structure of a real algebraic variety. Actually, it's an affine one. And the statement here is that S is contractible of general type. So of general type for an affine surface means that its logarithmic Codera dimension is maximal. In other words, kappa of S equals 2. So this is the part of the statement due to Ramanujan. So that this guy has the same topological properties as C2, but it's not C2 because it's of general type. And S over R is diffeomorphic to R2. And well, this is the part I can just try to explain to you. So we are in this first Dubouloz surface, and the set of, I showed you earlier that the set of real point of this guy is just the Klein bottle. So we'll draw F1 as a Klein bottle. So the horizontal thing should correspond to the exceptional divisor of the blow-up, and now I'm making these identifications, right? I'm wrapping like this and like this to get a Klein bottle. And if I draw the proper transform of these two curves here, so the vertical things should be the fibers of the P1 bundle structure on this F1, and these fibers are the same as the line going from this point in P2. So if I try to draw the proper transform of Q, it would be a section of this, so something like that. And so that would be Q. And C should behave like a priori like this. Yeah, something like this. Right. So in this F1, I'm removing, do I have colors here? Yeah. So I'm removing the union of this. Wow, sorry. And this. So look, what is the complement of this in this Klein bottle? So going from here, it's attached to here, but it's also attached to here. And let me see, this part is attached there too, and this piece is attached to this one. So the complement is connected, right? Complement is connected. And well, if you play a little bit more with this picture, in fact, it's homeomorphic to a disk. Okay, so S of R is homeo to a disk. And well, since we are working with smooth infinity surface, this means that it is actually diffeomorphic to R2. It's diffeomorphic to R2. Okay. So I have at least two kinds of fake planes of very different flavor, right? One is contractible of general type, and the first one is just QA-cyclic and very far from being of general type, because here, if you look at the projection to the first variable, well, this is an A1 fibration, something we heard about in Professor Mianishi's talks. And so in particular, if x is non-zero, then you can just say that z is y cubed minus x over x squared. So when x is non-zero, it just looks like a base cross A1. So here the Codera dimension is negative. Okay, now the game is try to classify. Okay, so what can we do? Well, I guess it's pretty clear what you can try to do. As for usual surfaces, you try to argue by looking at Codera dimensions. Okay, so you have hope to do something for non-general type, usually, and for general type, where you cannot expect much by trying to find families of examples first. So let's see. Let me keep this. Now, classification. What do we want as a classification? So there are two ways of thinking about the type of classification of such object you would want. Well, there are one possibility, classify up to isomorphism of real algebraic variety. So as R schemes. Or natural thing to to do in real algebraic geometry if you are just interested in irrational point, real points, classify up to what is called a birational diffeomorphism. So what does it mean? Suppose you have x prime, well, x prime, real algebraic variety, then a birational diffeomorphism is a map so of real algebraic variety, which means that it is defined over R, and such that the induced map between the real points of x and, well, sorry, there is an x prime, maybe it's clearer now. So it's defined at every real point of x, and the induced map here is a diffeomorphism. Right. So this is just a diffeomorphism of C-infinity manifold, which is given by rational functions with poles only at pairs of complex conjugate points. Somehow, that's the idea. Okay. So this is much more flexible, right? For instance, all the thing I did consisting of blowing up pairs of complex conjugate points, removing pairs of complex conjugate points, etc. There are typical examples of birational diffeomorphisms. So this is essentially the interesting thing to do, but it's much more difficult than this, actually. So I'll give you an overview of what's available here and what are some results here and some open problems. Okay. So now, how do we attack this kind of classification problem? Well, we are looking at complex, first we are looking at complex surfaces which are q-acyclic, right? So the first thing is that S is complex q-acyclic. Now, there has been a lot of work by many participants to this conference on the classification of complex q-acyclic surfaces. So, in particular, what is known is that such an S is necessarily affine and rational. So, I should cite maybe Fujita and Professor Gurja for that, or Fujita for the affine part, even though it's more like a remark, but the rationality is really a big, deep thing. So, and in case there are not of general type, essentially there is known full classification. So, classification is known for kappa not equal to 2. And families of examples are known in the general type case. So here is a main basic strategy. Strategy is go through the classification and check which ones have a real structure. So there is something to do here. There are classified, we have construction for these, but as complex manifolds. So it's not at all clear which one can admit a real structure. Once you have it, for these, determine the real locus. Right? So once I have this, and I found something which is q-acyclic with a real structure, I have something which is minimal topology and a real structure. But I need to decide whether it's a real Euclidean plane or not. So I need to characterize the real locus of these things. And at the end, classify. Yes, but we know the classification as complex surfaces up to iso over R. So this is basically a problem of forms of real forms of complex QAS surfaces. And actually, such forms do exist. And this is one difficulty when you want to classify things. To have a real structure? Yeah, well, it's basically a cohomological question. So you want to find this anti-holomorphic involution. So it's a problem of Galois cohomology with value in the sheaf of holomorphic function, or C-infinity function. It's not the way actually we are working. Well, I'll give you an example which illustrates that kind of thing. So just one word about real forms. Just to give you an idea. So we are in CP2 again, and we take a three cuspidal quartics. So there are things like this. And there are essentially, if I'm not mistaken, all projectively equivalent over C. But they have different real models, because here you could have a real point, here another real cusp, here another real cusp. Or you could have a real cusp and a pair of complex conjugate points, cusps. This is possible, just find out an equation which does the trick. And now you look at the complement. Well, the complement is certainly QAcyclic. There is a real structure because both are defined over R, but there is no way the complement can be isomorphic. Okay. And well, fortunately, there are not real Euclidean planes here, because if you look at the complement, it's certainly not connected. The interior of the guy is a copy of R2, and the exterior is essentially a Möbius band. So this guy fails to be Euclidean plane. But I'll show you how to cook up Euclidean planes from this. So the tools we have to attack these things well, there are mainly topological ones. So idea of the tools. Well, the thing is, whenever we have an affine surface, we can, real affine surface, we can complete it into a smooth, real projective surface. And we can assume that the boundary is an SNC divisor defined over the real. So in fact, we have to study pairs XB, where X is smooth, real projective, and B is a real SNC divisor. Just a warning here. This doesn't mean that every component of B is a real algebraic curve. It could just be a pair of complex conjugate line crossing in a point in P2. So the two irreducible components are not defined over the real, but their union is. Right? Pairs like this are such that X minus B is the S you are looking for. And you have to understand what is the topology of S in terms of the topology of these guys. We know that this X is rational, so it dominates some P2 by a sequence of birational contraction over C. Over the real, it's slightly more complicated. And then we have to try to characterize when the real locus of a guy like this can be R2. And there is one basic topological tool for this. That's the only thing I will mention. So we have a natural map which goes from the free abelian group generated by the irreducible component of B, of a C. So it's a free abelian group generated, formally generated by irreducible components of B well, the divisor class group of X. Well, these are just Veil divisors, and I'm looking at their class in the divisor class group. And now, since we are working with something rational, well, this thing is nothing but the H2 of B is generated by the irreducible component. And since we are working with rational gap, actually this thing is essentially isomorphic to this by, you take a Veil divisor and you just look at his homology class. And now this fits into the long exact sequence of homology for the pair XB. And what you should get here, if I'm not mistaken, is H2 of XB, Z, which by Poincaré-Lefschetz duality is the same as H2 of the complement, which is S, right? And by universal coefficient theorem, this is the same as H2 of SZ. Well, it should be the free part, but this is an affine surface, so the H2 has no torsion, plus the torsion part of H1. Well, and for similar reason, here you get the free part of H1 of S. Okay? So, if you want something which is Z-acyclic, this guy must be an isomorphism. That's the idea. If you want Q-acyclic, it has to be an isomorphism after tensoring with Q. Okay. And now for the real locus. Well, two things. Since B is defined over R and X is defined over R, are Galois modules for the action. Of the real structure. So I can look at the Galois cohomology, right? And then the statement, the proposition. I mean, this part is classical knowledge from the theory of affine of Q-acyclic surfaces. It's just reformulated in terms of these groups instead of these ones, just for ease of translation at this level. S of R is R2, if and only if, what? Well, the real locus of the boundary is non-empty. This is important. Right, I'm starting from a projective surface. And I'm removing a boundary, but if I'm not removing any real point, the set of real points of S will be the same as the one of X, and it will be compact. So at least I have to remove something. And so we have this map, and this induces a map from the Galois cohomology group here. So the Galois group is Z2, corresponding to this to the involution of the real structure. And this has to be an isomorphism. So hidden behind this is the fact that whenever you have a Veil divisor defined over R, you can associate to it some kind of real cycle of half the dimension, which is essentially the topological class of its real locus. And then, well, it's some kind of abstract nonsense with exact sequences. But the point is, in many circumstances, this map is just obtained from this one by tensoring with Z2. So, in particular, if you start exactly what we did for the Riemann surface by a configuration of real curves, in P2 you just blow up real points. Then to understand this thing, you just have to compute that one and tensor it with Z2, Z over 2Z. So that's usable in practice. So that's the tools. And well, so and after that, you have to go through the classification and see what you can do with this. So I don't know how much time I have. It says 1 hour from quite a long. Yeah, right. Yeah. So I start now, right? No, tell me.
I think 15 minutes you start here.
Yeah. So I have 5 minutes?
Yes, yes, fine.
Perfect. So I will just give you one classification theorem and maybe one example of what to do for this birational diffeomorphism stuff. So elements of classification. For kappa is equal to minus infinity. Okay, so I could be very quick here by saying, okay, I restrict myself to Z acyclic or contractible surface negative colored dimension. Then, by a theorem of Professor Miyanishi and Professor Sugi, we know that on the complex side, the only model is C2. So the only thing that could happen is that my real algebraic variety is a real form of C2. But such non-trivial form do not exist by a result of Kobayashi. So if I restrict to Z acyclic thing, I have no fake plane at all of negative Caldera dimension. The only guy is A2R, right? But if I go to Q acyclic ones, well, the first surface I have shown is an example of something Q acyclic of negative Caldera dimension, which is a fake plane, right? So, and classification is the following. So let's call it theorem. Let S be smooth, real, Q acyclic surface of negative kappa. Then the structure theorem is the following. Then S admits an A1 fibration over A1. So this one is A1 R, and this is defined over R. So it's a real A1 fibration with the following property. With the following property. Or every let's call it pi minus 1 of x contains a unique irrational. So the fiber here is a union of components isomorphic to either A1R or A1C, and those isomorphic to A1C come in pairs, right? But what I'm saying is that a necessary condition is that in each fiber over an irrational point, there is precisely one component, which is A1 defined over R, and it has, and that's the crucial thing, odd multiplicity. So if you remember my first example, this surface, right? So the real A1 fibration is just the projection onto the first coordinate. And there exists exactly one fiber over a real point which is not a real line. The fiber over x is equal to 0, which is 3 times a real line, right? So the statement is saying, okay, that should be the local model everywhere. But what I could have done in each fiber is to add pairs of complex conjugate things, but well, they would contribute to the H2. So Q acyclic implies really this. And there is one subtlety there. Okay, as a complex surface, it has negative Caldera dimension. So we know by the lectures given by Professor Miyanishi that it should have an A1 fibration. Possibly not over A1, but over a curve. But since it is Q acyclic, there is no choice. The base curve is to be A1. But this fibration is a priori defined over the complex numbers, right? And here the really difficult part is to check that it's defined, that there is such a vibration defined over R. And this is a non-trivial thing. If you look into, again, CP2 is a standard structure, and Q is a conic without irrational points. So that could be something like this. Right. There is no real solution of this. Then CP2 minus Q is smooth QRcyclic of negative Codera dimension, in fact, and it's defined over R. In fact, you can find that H1 of S is E2. But there is no A1 vibration defined over the real on that guy. The reason is, suppose there is one, and look at the general fiber and take their projective closure. When the general fiber over a general real point would be A1, so in the compactification you see an additional irrational point, which has to sit on the conic. But the conic has no irrational point. Right? So you really have something to do to pass from there exists an A1 vibration on the complex model to this vibration is defined over the real. And that's the difficult part in this thing. And, well, just let me conclude by one example statement. This particular S is if B equivalent to C2, so A2R. This means that there exists a birational diffeomorphism in the sense I introduced, which send it to the plane. And so that's a meta statement. Because I don't have time to go to this. There exists Q acyclic fake planes diff B to A2R of every possible Codera dimension. In particular, there are QRcyclic fake planes of general type, which are birationally diffeomorphic to A2. But there is no, for the moment, there is no theorem like every QRcyclic fake planes is birationally diffeomorphic to A2. And for instance, the question is the Ramanujan surface diff B to A2. And we don't have much ideas of how to proceed because this is just saying that neither the topology nor the logarithmic Codera dimension are effective invariant to distinguish birational diffeomorphism classes. The point is this birational diffeomorphism involve more than just making blow-up and blow-downs of curves on point along the boundary. You are forced to blow up things in the open part, pairs of complex conjugate things, and contract back some other things. So at the level of the complex model, you are not preserving the affine surface. But the Codera dimension is an invariant of this open part. So if you change it, of course, it's no longer useful to classify. Okay, I'm done. Yeah, well, look, in that case, you look at the pencil generated by, well, just take on the complex case, right? You have this conic and you look at the pencil generated by the conic and twice its tangent line at a point. So you get something which is an A1 vibration with odd multiplicity. And the upshot is that in this case, the real locus is not connected. I mean, the complement of a conic with an irrational point. You have the inside of the conic and the outside. The inside is isomorphic to R2, and the outside is again a Möbius band. Same phenomenon as for this tricuspidal quartic. So odd multiplicity has to do with connectedness somehow of the real locus. Well, you know, you can ask this question for every field extension you want. The thing is, doing equivariant birational geometry when the Galois group is Z2 is much simpler than for an arbitrary group. Thank you.